there's new progress in controlled nuclear fusion, and this time it's from the US-based TAE Technologies. Recently, the company unveiled a revolutionary new reactor design that completely breaks away from the traditional Tokamak configuration. It's said to have a power output 100 times that of its Tokamak counterparts. Hard to believe, right? When it comes to attracting investment, no one does it quite like American companies. TAE Technologies has been at it for 27 years and is still in the design phase. Despite once aiming to roll out a commercial prototype by 2030, which isn't far off now, they're yet to reach that milestone. Let's take a closer look at what this innovation is all about. For controlled nuclear fusion, the most well-known reactor configuration is the Tokamak, which is also the most widely adopted design globally. Examples include the International Thermonuclear Experimental Reactor ITER, China's Experimental Advanced Superconducting Tokamak East, the HL2M Tokamak, and Energix, which we've covered multiple times. These reactors vary mainly in size. Private enterprises often opt for high-temperature superconducting materials and may be more aggressive in certain basic modules, but overall, the Tokamak remains the mainstream choice. However, TAE's reactor, based on the field reversed configuration FRC, looks nothing like the fusion devices we're familiar with. A Tokamak uses toroidal, colloidal, and central coils to create a magnetic cage that confines the plasma. Clearly, its magnetic field forms a closed loop. In contrast, the FRC features an open-loop design. In the FRC diagram, the green lines represent the magnetic field generated by the external coils of the fusion device, while the blue donut-shaped ring is the plasma. Driven by an external force, the plasma generates a toroidal current, indicated by the brown arrows. This toroidal current, in turn, produces its own magnetic field. The axial component of this self-generated magnetic field inside the plasma opposes the external magnetic field, hence the name field reversed configuration. The interaction between the internal and external magnetic fields leads to magnetic reconnection, enabling the self-organization of the plasma. In theory, as long as the toroidal current persists and maintains sufficient strength, the FRC can remain in a steady state. Picture two magnets facing the same direction with a third magnet in between facing the opposite way. The middle magnet stays in place. But achieving this stability in practice is extremely challenging. Unlike the Tokamak's closed-loop magnetic field, which can pull the plasma back no matter which way it drifts, the FRC's open-ended design allows for abnormal transport. Ions and energy can rapidly escape along the axial direction. Thus, effectively confining the plasma behavior is a crucial challenge in actual FRC devices. You might wonder, why bother with this configuration when the Tokamak is already a well-established and mature technology with a wealth of accumulated knowledge? The key lies in the FRC's exceptional parameter, the beta value, which represents the ratio of plasma pressure to magnetic field pressure. The FRC has an average beta value as high as 90%, while the typical beta value for a Tokamak ranges from 5% to 10%. This significant difference means that the FRC can confine plasma of the same volume or density using a much weaker magnetic field. Since magnetic fields are generated by energized coils, the FRC requires far less energy, which contributes to improving its Q value, a measure of a fusion device's performance. With fewer coils needed, FRC-based fusion devices can be more compact and streamlined. TAE's latest design, Norman, is even smaller than its predecessors, highlighting the FRC's distinct advantage in miniaturization and, consequently, significant cost reduction in manufacturing. TAE has been persistently exploring nuclear fusion based on the FRC, despite its higher difficulty level and greater academic uncertainties compared to the Tokamak. However, a breakthrough in this area could greatly enhance its appeal in the capital market. A crucial aspect of the FRC-based fusion technology is its focus on advanced fuels, specifically hydrogen-boron fuels. From the plasma perspective, it involves the reaction between hydrogen nuclei protons and boron-11 nuclei. The fusion process begins with the combination of a proton and a boron-11 nucleus to form a carbon-12 nucleus, which quickly decays into 3 helium-4 nuclei alpha particles. Each alpha particle carries an average kinetic energy of about 2.9 mega electron volts, and the entire reaction releases 8.7 mega electron volts of energy. In fact, the company's name, TAE alpha energy, is derived from these 3 alpha particles, reflecting its long-standing focus on advanced nuclear fuels rather than the currently dominant deuterium, tritium-D fusion. So, what makes hydrogen-boron fuels advanced? The answer lies in their near absence of neutron emissions during the fusion process. While some neutrons may be produced through side reactions, their amounts are negligible. In the deuterium, tritium-D reaction, high-energy neutrons are emitted. Capturing the energy released by fusion largely depends on these neutrons. For instance, lithium metal is often used as an absorption layer. When bombarded by neutrons, lithium releases heat and also enables fuel breeding. However, since neutrons are neutral particles, they can't all be efficiently captured. This poses a significant challenge to the materials lining the reactor's vacuum chamber, as they must withstand constant neutron bombardment. In contrast, the only substantial particles produced in the hydrogen-boron reaction are alpha particles. As positively charged atomic nuclei, alpha particles can be precisely controlled using electromagnetic fields. This property allows for direct conversion of their kinetic energy into electrical energy. In an electrostatic direct conversion process, for example, when high-energy alpha particles leave the plasma and enter an electric field, their kinetic energy is converted into electric potential energy as the field slows them down. The resulting potential difference can then drive an external circuit, generating direct current. The theoretical efficiency of this energy conversion method ranges from 60% to 80%, far surpassing the 30% to 40% thermal efficiency of the D-T reaction, where lithium captures neutron-generated heat to drive steam turbines. This direct conversion minimizes energy losses during the conversion process, complementing the FRC's design advantage of miniaturization. Since it bypasses the need to convert heat and mechanical energy into electricity, FRC-based devices require fewer mechanical components, creating a mutually reinforcing benefit. So, why do Tokamaks still rely on fusion instead of hydrogen-boron reactions, given the latter's potential for direct energy conversion? The answer lies in the fundamental differences in plasma conditions each design can support. Tokamaks operate with thermal plasma that follows a Maxwellian distribution, meaning all particles within the plasma are in thermal equilibrium and have approximately the same temperature. For fusion, the reaction cross-section peaks at around 100 million degrees Celsius 100 mK, a temperature that, while challenging, is currently achievable with continuous optimization of plasma control. Researchers aim to meet the so-called fusion triple product criteria to achieve sustained fusion. Hydrogen-boron fusion, on the other hand, has a much lower reaction cross-section. It only reaches its peak at a staggering 1 billion degrees Celsius 1 JK. Reaching such extreme temperatures in a tokamak is extremely difficult. Moreover, hydrogen-boron fusion occurs in non-thermal plasma, deviating from the Maxwellian distribution. In this state, the average plasma temperature remains relatively low, but a subset of high-energy particles can reach the required 1 JK. These high-energy particles are responsible for the fusion reactions and energy release. Precisely controlling these high-energy particles represents a major challenge for any fusion device aiming to utilize hydrogen-boron fuel. This is where the FRC's high beta value reaching up to 90% gives it an edge. With a high beta value, the FRC can maintain significant plasma pressure using a relatively weak magnetic field. This makes it more feasible to reach the 1 JK temperature required for hydrogen-boron fusion compared to a tokamak. To achieve the same temperature, a tokamak would need an impractically strong magnetic field due to its lower beta value 5 to 10%, highlighting why TAE Technologies chose the FRC configuration from the start. Their focus on hydrogen-boron fusion dictated a fundamentally different approach to device design. TAE's recently published research demonstrates further progress in optimizing their device design, with the most notable advancement being enhanced miniaturization. Public reports indicate that TAE has previously achieved a peak temperature of 75 million degrees Celsius 75 mK and sustained plasma conditions for 10 milliseconds at lower temperatures. Even if their latest experiments have improved these metrics, they still face a vast gap compared to the 1 JK temperature and the desired control timescales ranging from microseconds to seconds. Over the past 2 decades, TAE has undoubtedly amassed extensive expertise in FRC-based fusion and made continuous technical breakthroughs. However, compared to the maturity of Tokamak technology, it still lags significantly. This raises doubts about whether TAE's goal of launching a commercial prototype by 2030 is more of a strategy to attract investment rather than a realistic short-term objective. The ultimate question remains, which approach, FRC or Tokamak, will achieve commercialization first? Overall, Tokamaks appear more promising in the short term. With a 70-year research history and over 200 operational devices globally, Tokamak technology is on the verge of achieving a Q value greater than 1, a crucial milestone for practical fusion energy. While the FRC shows long-term technical potential with its innovative design and advanced fuel choice, it also carries substantial risks. Currently, the development of FRC-based fusion is primarily driven by private enterprises, lacking the global collaborative efforts and government support that have propelled Tokamak research. Although companies like TAE have secured investments from tech giants such as Google and Jeff Bezos and engaged in technical exchanges with leading research institutions, the overall scale of FRC research remains limited. This isn't due to a lack of interest from research institutions or governments. Instead, many physical models underlying FRC-based fusion are still in development, and the available experimental data isn't yet compelling enough to attract large-scale public investment. Given the slow pace of progress in this field, only private enterprises, buoyed by venture capital, can afford to conduct limited research. We've previously covered another company, Helion Energy, which also uses the FRC concept but has adopted a pulsed operation mode to simplify the design, as opposed to TAE's pursuit of steady state control. Helion's approach may seem more achievable in the near term. Whether these companies can make significant breakthroughs in the next decade remains a captivating area to watch, as it could reshape the future of fusion energy.